I am Shailendra Singh Ojha, Assistant Professor in Department of Electronics and Communication Engineering. Today I am going to discuss high frequency model of Mosfet. That there are two devices, one is BJT and another one is Mosfet. And primarily these two devices are used as an amplifier, and not surprisingly, but these two devices behave differently at low frequency and at high frequency. At low frequencies, capacitive effects are negligible, and at high frequencies, various capacitive effects comes into existence. And due to that, the low frequency model of BJT and Mosfet is somewhat modified. In previous lecture, we have already discussed high frequency model of BJT. Now let us talk about high frequency model of Mosfet. Mosfet, all of you know, metal oxide semiconductor field effect transistor. One thing that we also remember about Mosfet is its input impedance is infinite. Practically it is very large. So due to that, no current flows into the gate. That means from input side, if you will see, then current will be 0. In other words, I can say that input current is equal to 0. This is gate terminal, drain terminal, source terminal and body terminal, and various capacitances exist between various terminals, and its equivalent or its simplified model can be considered as this one. And for the more simpler approach, or the model which is explained here can also be considered, because this CDB can be neglected and its effect will be very less. Negligible effect will be there if you will consider CDB. So this is the most used model for the high frequency analysis. And here you can see, if I will omit these two capacitances, that means CGD and CGS, that means capacitance between gate and drain and capacitance between gate and source, then this model will convert into the low frequency model. And GM is the transconductance, VGS is the voltage across this capacitor, and this is the R0. So this is the model of Mosfet. Now for its analysis, just like BJT case, we need to find out two parameters. One is FT, that is unity gain frequency, and another one is the high cutoff frequency, FH. So let us discuss these one by one. If you will concentrate on this circuit, then we have considered inputs, current source II, VGS, and everything we can see here very clearly. And the current which is flowing through this capacitor will be VGS and multiplied by SCGD, and this is the output current. So if you will see here, then what is I0? I0 is equal to, actually there are two currents, one current is this, another current is this. These two currents are approaching at this node and this current is going from this node. So if you will apply KCL, then we can easily find out that I0 is equal to GM VGS minus SCGD. This current minus this current, then you will get it. And CGS is actually considered here, and CGD is very small, at the high frequency. So we can neglect this term and you can find out I naught is nearly equal to GMVGS. So if you will see, then you can easily find out that VGS is equal to SCGD plus SCGS. Okay. That means input current multiplied by the impedance which is provided by these two capacitors. So we can easily say that that VGS is equal to II upon SCGD plus CGS. So I naught, we have found out this. II can be found out by this because II will be the multiplication of VGS and CGS plus CGD. So if you will put here, then VGS and VGS will be cancelled out and you will get I naught upon II is equal to GM upon SCGS plus SCGD. And we all know that S is equal to J omega. So we can find out, we can put value of S is equal to J omega. And if you will find out its magnitude, then magnitude will be equal to Gm upon omega CGS plus CGT. Now, when this frequency will become unity, we can easily find out from this. That means, not frequency will become unity, I mean to say that when we can find out unity gain frequency, when gain becomes 1. When gain becomes 1, that means this factor will become equal to 1 and omega will be denoted as omega t, which is nothing but unity gain frequency. So in this way, you can find out that omega t is equal to Gm upon CGS plus CGT. And yes, omega t is equal to 2 pi ft. So you can easily find out that ft is equal to Gm upon 2 pi CGS plus CGD. So in this way, you can easily derive an expression for the unity gain frequency. Now next we are going to consider the common source amplifier, and from this common source amplifier we will find out this high cutoff frequency. So let us approach towards this derivation and let us try to find out the high cutoff frequency. We have applied signal voltage, its internal resistance R signal. This is RG VGS, and actually this is the high frequency model of Mosfet. And every other than this, all the resistors and this voltage are the externally connected components. So we can draw its equivalent. That means we can consider these three resistances together and it can be represented as RL dash, and its RL dash will be equal to small r naught in parallel with RD in parallel with RL. And now input side, if we will see, then we can approximate this. This is will be as such GMVGS, CGD, CGS, and we have approximated this. That means what will be the voltage at this across this resistance will be V signal into RG upon RG plus R signal multiplied by V signal. So it is simply obtained by voltage divider rule, and equivalent resistance of these two will be the parallel combination of these two. From the frequency response of BJT, that in the midband gain is almost constant and it is independent of the capacitor value, because CGS and CGD can be considered as 0. So midband gain will be equal to AM, which will be equal to V naught upon V signal. And if I will explain from here, then what will be the output voltage? This GM VGS multiplied by this RL dash, because this current is flowing through this resistor, and negative sign will be obtained because current is flowing like this and we are finding out V naught like this. And what will be the signal voltage that we have already find out from this. So now we can find out the ratio of these two, and it will be equal to minus Rg upon Rg plus R signal multiplied by GMRL dash. Okay. And V naught I have already explained, and RL dash is the parallel combination of these three. So now actually for its more analysis, we need to find out the effect of this capacitor, and it will be represented as C equivalent, this capacitor, because this is coming towards input side as well as corrected towards output side. So with the help of Miller's theorem, we can find out the C equivalent as CGD into 1 plus GMRL dash, and the combination of these two will be the input capacitance. So, and rest everything is same, and soon we will come to know that why does we are obtaining the response like this. Once you will find out this cutoff frequency, because in the midband gain is constant and at higher frequency it decreases, and this is the point where gain decreases by minus 3 dB. So, if you will recognize a single time constant circuit of low pass type, then VGS will be equal to Rg upon Rg plus R signal into V signal and into 1 upon 1 plus S upon omega naught. This is from the response of low pass filter. And omega naught is 1 upon C in into R dash signal. R dash signal, I think all of you must aware of R dash signal. This is the parallel combination of R signal and Rg. And C in, you have already found out the combination of CGS and C equivalent, this is CGS, and C equivalent is this, which is which has been found out with the help of Miller's theorem. So now we can write it as CGS plus C equivalent is this, and R dash signal is R signal in parallel with Rg. So now you can write V naught upon V signal, that means the expression for the high frequency gain is equal to V naught upon V signal minus Rg upon Rg plus R signal into GMRL dash upon 1 plus S upon omega naught, where omega naught is 1 upon C in into R dash signal. And if you will see, other than these all things are constant. Rg is constant, R dash signal is constant, GM is constant, RL dash is constant. So we can represent it as AM, and AM is nothing but the midband gain upon 1 plus S upon omega h. So omega h is equal to omega naught, which is 1 upon C into R dash signal, which is the high cutoff frequency. And if you will plot its response, then its response will be like this. So if you will go through some numericals, then numericals can be like this. Find the midband gain AM and the upper 3 dB frequency FH of common source amplifier fed with a signal source having an internal resistance R signal is equal to 100 kilo. The amplifier has Rg is equal to 4.7 mega ohm, Rd and Rl both are equal to 15 kilo ohm. GM is already provided, which is 1 milliampere per volt. R naught is 150 kilo ohm. CGS is 1 picofarad and CGD is 0.4 picofarad. These type of numericals seems to be very complicated, but if you remember few relations, then these are the simple numericals which can be solved with the help of the derivations, with the help of formula which we have already derived. You know, AM is equal to minus RG upon RG plus R signal into GM RL dash. So, just try to remember few things, the approach to solve this type of circuits. First of all, find out RL dash, which is the parallel combination of R naught, RD and RL. These three are provided: RL, R naught and RD. Put these values, you will simply get 7.14 kilo. GM RL dash, GM is provided. You have already found out RL dash. Put this here. You will get GM RL dash is equal to this. Now simply put this value and RG and R signal value into this expression to obtain AM. And the value of AM is now minus 7. Now the equivalent capacitance C equivalent, it can be found out with this relation 1 plus GM RL dash into CGD. So that's why I'm saying that first of all find out GM RL dash. To find out GM RL dash first find out RL dash. RL dash, then GM RL dash, then AM, and then C equivalent. So if you will put these values, we have all values. So this is simple mathematical calculation. And we will obtain C equivalent is equal to 3.26 picofarad. Now the total input capacitance is equal to CGS plus C equivalent. C equivalent we have already found out. CGS is already given. So this C in will be equal to 4.26 picofarad. Now, why we have found out these C in and R signal just to calculate the value of FH. FH is equal to 2 pi C in into R signal in parallel with the RG. Now we have found out these all values. So you can easily find out FH also. So FH will be this, and next is the transmission with zero frequency. That means the frequency at which no signal will be transmitted, and it is Fz is equal to Gm upon 2 pi CGD. If you will put, it is 398 megahertz. And if you will see, this is 382 kilowatt. That means this frequency is almost 1000 times to that of upper 3 dB cutoff frequency. So now you can conclude that Fz will be how much? It should be very, very, very large in comparison to FH. Now, this is the frequency response of amplifier. Generally, if you will see, then at lower frequencies, gain is low and it increases as frequency increases, and then it becomes constant and again it decreases. So, at lower frequencies, these frequency ranges are known as low frequency band. This is mid band and this is high frequency band. And at lower frequencies, the gain decreases just because of the effect which is known as coupling capacitor and bypass capacitors effect. These are effective at low frequencies and gain decreases at these frequencies. And at high frequencies, gain falls due to internal capacitive effect. That means here CGS and CGD. So these are responsible for the fall in gain. And here you can see, if you will couple or if you will connect more than one amplifier together, then gain will decrease, gain will keep on increasing, but bandwidth will decrease. If this is gain, this is frequency, then this variation will be like this. For example, this is 1 amplifier, 2 amplifier, 3 amplifier, and it will happen like this. So you can see here that bandwidth decreases. That means lower cutoff frequency is shifting towards high frequency and higher cutoff frequency shifting towards lower frequency. This is why the bandwidth decreases. And new lower cutoff frequency and higher cutoff frequency, you can find out by these relations, where FL is the old lower cutoff frequency, FH is the old higher cutoff frequency, and N are the number of amplifiers which are cascaded together. So in this way, we can find out new bandwidth, new lower cutoff frequency, and a new higher cutoff frequency. Thank you.